Hello and welcome back everyone to another Telcos Get Technical podcast here at VMware. I'm your host Anupama Mahabhashyam, Senior Technical Product Marketing Manager. With me today I have my co-host Steve Hoynish, Senior Technical Marketing Manager. The RAN Intelligent Controller or RIC is likely to be cornerstone of Open RAN deployments. It's a controller running multiple applications that underpins the Open RAN premise. But how should telcos think about this deployment and use both the near real-time RIC and non-real-time RIC with their respective XApps and RApps?
Joining us today to explain more about the RAN Intelligent Controller is our esteemed guest Rakesh Misra, Director of R&D Engineering in VMware's Service Provider and Edge Business Unit, where he leads the team that is developing Open RAN solutions. Before joining VMware, he co-founded Uhana, which commercialized an AI ML platform for mobile radio access networks. Uhana was acquired by VMware in 2019. Welcome Rakesh, and thank you so much for joining us in the session today. So let me ask you first, you've been working on the RAN intelligence for over a decade now. Can you tell us how it all began?
Yeah, sure. Thanks, Anupama, and thank you, Stephen, for inviting me to this very exciting podcast series. And hello to all the listeners. Yes, indeed, it has been over a decade. My journey with RAN intelligence began sometime around 2012, 2013, when I was doing my PhD at Stanford University, where I was working on understanding the common performance and quality of service issues in radio access networks and looking at how we can use data and AI/ML techniques to address them. There was this one time where we managed to get a data set from a tier 1 US operator from a stadium in the Bay Area. So this operator had a deployment inside the stadium where they had divided the seating area into 40 zones. And they effectively had a cell site in each of these zones with 3 carriers each, that is 3 frequency layers each. So there were a total of 40 times 3, that is 120 cells across all the seating areas. We got a data set from this deployment during the course of a couple of NFL games, when the stadium is packed with people. And this was subscriber level trace data, not the performance management PM counters that we commonly use for studying performance, but a richer, more fine-grained version of performance data. Every time a user goes through an event with the radio access network, a trace or a record of that event is generated by the network. So when a user sends a connection request to the RAN, there's a trace event that gets generated by the network containing the details of that request. When a successful response is sent to the request, there's a trace event that is generated containing the details of that response. When the user starts, when a new bearer is set up for a user or a bearer is released for a user, there are trace events that get generated. Every time a bearer gets released, there are traffic reports that get generated. So as you can imagine, the trace data contains a very rich, very fine-grained information about the radio access network. So we got this data, we started looking at it. And the first observation we made was that the quality of service that the users in the stadium were experiencing during the NFL games, the downlink throughputs and uplink throughputs were very poor. They were getting on the order of hundreds of kbps of throughput, not even 1 mbps for the large fraction of the sessions. And on first thoughts, we thought this is expected, right? There are so many people packed in the stadium, all contending for the limited network resources in the stadium. So it's kind of obvious that they would suffer in terms of the throughputs that they're getting. But then when we continued looking into the data, we found something that turned this into a mystery. When we looked at the spectrum utilization, the PRB utilization across all the 120 cells in the network, we found that it was not even reaching double-digit percentage. Meaning more than 90% of the spectrum resources, PRB resources in that deployment were actually not being used. And yet the subscribers were experiencing a very poor quality of service. This did not make sense at all. I mean, why would you not use your available resources? And then when we dug further into the data, what we discovered was something very shocking, very interesting. We found that for some reason, maybe because of how the antenna tilts were configured or how the coverage was shaped, only a few cells in the network were attracting the majority of the users to connect to them. Something like 20% of the cells were carrying 80% of the traffic, and the remaining 80% were heavily unused or underused, right? And even as a PhD student, I could immediately think of a very simple improvement to the algorithm, right? That would significantly improve the performance that network could deliver to the users in the stadium, right? So this is what got me started on this journey. And also surprising was that the RAN equipment in this case was provided by a tier 1 RAN vendor. Right? We tend to think that RAN equipment provided by the incumbent vendors who have been in business for decades must be super well optimized, right? Wrong. Even with these vendors, when it comes to the intelligence in the RAN stack, there's actually a lot left to be desired. There's a lot of room for improvement. And that is what got me started on this journey. I started thinking about how we can make the intelligent in the radio access network better, so it performs better, and how we can enable the ecosystem, researchers like myself, other innovators in the industry, to contribute to improving and advancing the intelligence in the RAN.
So Rakesh, let's fast forward 10 years or so to 2023. The industry has now defined a RIC to solve some of those problems that you mentioned. What is this RIC after all? Can you step back for a second and explain the RIC?
Yeah, absolutely. So the RIC, or the RAN Intelligent Controller, is a new network element that has been defined by the O-RAN Alliance in its reference architecture for Open RAN. And there are actually two variants of the RIC. There is what is known as a near real-time RIC, and there is also what is known as a non-real-time RIC, which are two different network elements. So to understand what the RICs are, we need to first understand the RAN software stack a little better. So if you think about how a RAN software stack is architected, a RAN software stack consists of two broad categories of functions. On one hand, it has a set of data processing functions, which in networking jargon is sometimes known as a data plane. It has a set of data processing functions which process user data, and this is based on 3GPP specifications. There's a set of protocols like RRC, PDCP, RLC, MAC, and PHY that are implemented by the vendors. And these data processing functions are quote unquote dumb, meaning they don't have any inherent intelligence. They do expose some configuration. There's some parameters configuration that can be set about them. But once those parameters have been set, and when user data flows in at runtime, there is a fixed, predetermined way of processing that they do on the user data. So the data plane themselves are just quote unquote dumb data processing functions. But complementing these data processing functions is a rich set of algorithms that actually contain the intelligence for the radio access network. And these algorithms are the one that tell the data plane how they should process user data. These algorithms are the one that set those configurations or the parameters that the data plane processing functions expose. So they are instructing the data plane how they must process the user data. And these algorithms, in networking terminology, we call them as the control plane or the management plane of the network. Control plane for the set of algorithms that need to run at faster timescales, under a second. And the management plane for the algorithms that run at slower timescales, slower than a minute or slower than a second, right? And these algorithms actually have a direct influence on how good a quality of service the RAN is able to deliver to its subscribers, how spectrally efficient the RAN is, and how operationally efficient the CSP, the operator, is in operating its radio access network. And traditionally, in the RAN solutions or RAN equipment that the incumbent RAN vendors have provided, these algorithms are tightly integrated with the data processing functions. The control and management plane are tightly integrated with the data plane. And as part of the Open RAN transformation, the O-RAN Alliance, the industry, is attempting to decouple this intelligence from the data plane processing functions, decouple the control and management plane from the data plane. And not just that, also allow third parties to build some of these algorithms, some of these control plane and management plane functions. And this is where the RAN intelligent controller comes into the picture. The near real-time RIC is designed to be the control plane platform. It's an abstraction layer that sits between the RAN data plane on one side and the intelligent algorithms, which now third parties can provide in the form of what are known as XApps on the other side. So it's an abstraction layer that sits between XApps and the RAN. Right? And similarly, there is a non-real-time RIC, which acts as the management plane platform. It's an abstraction layer that sits between the RAN data plane on one side and the intelligent management plane functions that third parties can now provide in the form of what are known as RApps. And the RIC basically becomes a platform for hosting these third-party XApps and RApps. Right? So that
Rakesh, let me ask you there. So what kind of use cases can third parties bring to the table then by using the non-real-time and real-time RICs? What would be some of the technical and business drivers from their perspective, and perspective of these third parties, and why should CSPs care about this? So why, what would lead the CSPs to care about using the RIC and these RApps and XApps? Maybe you could talk a little bit about that for a sec.
Yeah, so I see there are three main categories of use cases that are developing in the industry, and these correspond to three main categories of technical and business drivers for the use cases that can be built, these XApps and RApps that could be developed on a RIC platform, be it near real-time or non-real-time. And I shorthand these three categories as optimization, monetization, and automation. So the optimization category of use cases refer to the use cases whose primary technical goal is to improve or optimize the quality of experience or quality of service that the network is able to deliver to the subscribers. So this would include, for example, a traffic steering or load balancing application, which would solve the problem that we discussed at the start of this podcast session. So these optimizations could be generic for any kind of user, any kind of traffic, or there could be traffic specific optimizations. For example, you could have use cases that perform VoNR, voice over NR specific optimizations, or use cases that perform IoT specific optimizations. And ultimately, the business driver for this category of use case is to help the CSP improve their customer retention and improve customer satisfaction. Right? The second category of use cases, the monetization category, is about creating new revenue streams for the CSP. So CSPs, as you know, are making a lot of investments into 5G. And their biggest source of revenue, which is what they charge us, the wireless subscribers, for our 5G plans, is stagnating. We are already paying almost as much as we would be willing to pay for our 5G wireless plans. So how do CSPs recover the investments that they're making into their 5G networks? They need to find new ways of revenue, new revenue streams, new monetization opportunities. And the RIC provides one vehicle to create new monetizable capabilities for themselves. And there are a variety of use cases that the industry is working on. For example, SLA assurance for network slicing. So with SLA assurance for network slicing, CSPs can provide a new service to subscribers who are willing to pay premium in return for getting a dedicated slice of the network with guaranteed SLAs. Another use case is precise location. So in areas where GPS doesn't work well, so think of factory floors in the basement or warehouses, or even in dense urban areas where there is no good line of sight to the sky, the RAN provides an alternative means for inferring the 3D location of a device, and there can be XApps and RApps that can infer the location of devices in the network. And the CSPs can expose this location as an API to any external location-based service that is willing to pay to use this API. So this is a family of use cases which are really aimed at creating new revenue streams for the CSPs. And the third category is around optimization. And the use cases in this category are all about automating the manual operational tasks that the operations teams of CSPs do on a day-to-day basis to operate and run the radio access network. So things like automating how the physical cell identity, PCI, is configured automating how conflicts in PCIs are detected and resolved, how RATS configuration is set, how coverage and capacity parameters are set, automating how subscriber issues in subscriber KPIs are discovered, automating finding the root cause of the subscriber issues. So there can be a suite of applications that the industry can now build on top of the RIC platform to automate several manual operational tasks in the network. And the business driver for this category of use case is ultimately to lower the OPEX, the operational expense of running a radio access network. And this might bear some similarity with SON, self-organizing networks or self-optimizing networks that we have seen earlier. But what the RIC allows us to do is way more powerful and allows us to introduce much novel forms of automation into radio access networks.
That's great. So it's good to know what are the drivers for the CSPs, right? Another thing is, like, many people say that RIC is just an advanced SON. Is it even a useful assessment?
Is RIC just advanced SON? Well, are cars just advanced horses? Maybe a little bit, yes, but largely no. Yes, it is correct that the RIC shares some similarities with SON. The idea of bringing automation to RAN through software applications and the idea of having SDKs and API for developing these applications, we have seen them in SON systems. But to say that the RIC is just advanced SON, in my opinion, would be grossly under-characterizing the RICs. So with SON, what CSP said was, hey, we have deployed a complex radio access network, and we have a ton of complex manual things that we do on a day-to-day basis to operate these networks. Can we use software to automate some of these manual operational things? That was the idea of SON. With the RICs, we are looking at a new way to build the RAN itself. Yes, we can use the same RIC to also automate how the RAN is operated. So I see SON as just one use case or one category of applications that now could be developed on the RICs. But what the RIC enables goes far beyond SON, how it allows you to program the deeper layers of the RAN, the RRM algorithms in the RRC layer, and even the scheduler algorithms in the MAC layer with the near real-time RIC. That would be unthinkable for SON. The scale at which RICs aim to incorporate AI/ML natively into the RAN, it's beyond the scope of what SON was designed for. The kind of data that RICs expose to developers with subscriber level data, trace data via the non-real-time RIC, and very near real-time user and cell data via near real-time RIC, that's incredibly more powerful than the simple PM counters and FM counters that SON systems work with. And this means that the kind of applications that can be developed on the RICs is incredibly more powerful than what could be done with SON systems. And finally, the kind of cloud native and CI/CD mindset and our approach that RICs bring to RAN programmability, that's beyond the realm of SON. So going back to your question, yes, RICs have some similarities with SON, but I think they can replace SONs going forward, and they have a much grander vision and purpose and are incredibly more powerful than SON systems.
That's excellent, Rakesh. That's a great explanation. Do you have any other final remarks about how the RICs offer a new paradigm for innovation in the RAN?
Yeah, absolutely. So with the RICs, we need to understand that this is for the first time ever in the history of commercial RAN, in over 4 decades that commercial RAN have been in existence. For the first time, third parties, external entities can now program the intelligence in the radio access network. This could be smaller companies, startups, universities, research organizations, or even individual developers can now build XApps and RApps to program the deeper layers of the RAN. They can compete to push the frontiers in subscriber quality of service, spectral efficiency, and innovate in new kinds of monetizable services for operators. So this is a very exciting time. VMware, in fact, last year launched a RIC partner program. And in just over 6 months, we have 20 companies who have joined us and who are now using the VMware RIC to develop various XApps and RApps for the RICs. And I expect this ecosystem will grow to hundreds in the coming year or two, and maybe thousands in 5 years from now. So it's a really exciting time ahead for the radio access networks and for programmability and intelligence in radio access networks.
Yeah, thank you for joining us today and sharing your insights on RIC as always, Rakesh. Appreciate it. And thank you so much, Steve. And we'll see you again. Take care, everyone.
My pleasure. Thanks for having me.
Thank you.
Thank you.